There's something I'm missing that's not worth finding out.
I spent my whole first time working on that too, basically working out.
All right. Before I start answering your questions, I want to show you these waveguides. I'll pass these around. This is a standard kind of waveguide connector you get. This is something that split a signal, and this is an X-band waveguide. I'll pass these things around. So that's a standard short guide. This is a horn that would be matched on that. That's the X-band waveguide. This would be the horn that would match to an antenna. That would just give it fairly high gain 6. We'll get to antennas later, but it focuses the electromagnetic energy. That's all an antenna does. And this is really a slotted waveguide. You can see the slot in the center. It's used for really when we do demonstrations and stuff. But this is it's a lower frequency guide. Now, the way you always tell the frequency on a waveguide, the cutoff frequency, you look right there, and that width is lambda over 2. So you can figure out the cutoff frequency for the waveguide. You all follow me, class? That'll do it every time. And these are all standard rectangular guides. There are cylindrical guides. They're less common. But has anybody ever opened up your microwave oven and taken a look at the microwave generator? All right, you'll see a waveguide like that feeds right to the actual chamber. And there's a lot more to this than just opening it up like that. You have to impedance match. We'll get into that. But that's really what waveguides are in a nutshell. If we're talking about conducting, they call them perfect electrically conducting waveguides. Now, I also have some stuff here. People who haven't picked up their quizzes. Let me see if I can get this. Is Christopher Blake Stafford here? All right. Is sure, Patricia Phillips, I think, or Patrick Phillips, sorry. Here? Is Peng Fei Liu, L-I-U here? Logan? There's 2 coming down. You'll get paid. This one's yours too, isn't it? Oh, I'm sorry. I couldn't. Sorry. Brian Reyes, Tucker Snell, and Logan Tyler Smith. Sorry. Forgive me if I mess up your name. Peng Liu, L-I-U. I figured I'd try to get them all here. So I want to tell you, before I get into answering questions, I sent everybody a YouTube link. You should have gotten this. I just sent it to you. And this is a great video on slab waveguides. The guy does a great job going through it in a way that's meaningful and understanding. You can understand it. I'm going to go through slab waveguides, but I'm going to tell you, some of these equations get a little tedious. There's a lot of them, and he kind of summarizes stuff pretty well and gives you some good videos. I have a PowerPoint or 2 here where I may put it up before I just run through the equations and show you certain things about slab waveguides and then fiber optics. But before I do all that, does anybody have any questions about the homework I gave you? How many tried the homework? Okay. Did you get it? Yeah? What's wrong, sir? What does that mean? You kind of sort of did. Did you get the right answers? I gave you the answers, right? You got them? Okay. They should work out. Those are the right answers. And But you see what's going on here. The waveguide simply replaces a transmission line. The big difference is the characteristic impedance of the guide. You have to know it's almost always the 1-ohm mode for a rectangular guide, and you have to know your frequency operation. Then after that, you have to make sure you get beta in the guide, beta Z, I call it, or beta along the guide, correct. And then put it in those waveguide equations, and it'll work every time. You won't have any problems. But I want to warn you about one thing. Those equations, students make more mistakes solving those equations on a calculator than any others I've ever seen. So make sure you can do it and do it accurately, because it's easy to mess up. Y'all know what I'm talking about? That's that Zn equation is equal to Z naught times ZL plus J Z naught tangent of beta times L, but that beta is beta in the guide over Z naught plus J ZL times tangent of beta in the guide. Just warning you about that thing. Yeah.
Can we go over how to get the voltage at the source for that same
Source.
problem? Voltage at the input to the waveguide.
All right, we'll do it. Yeah, we might as well just talk about this. Some of you haven't done this, and this is going to really it'll overwhelm you if you don't keep up with this. So what I have is this. You're going to have some RS. You're going to have a voltage source here, some VS. This will be a phase, magnitude and angle. Then you're going to have your waveguide. I'm just going to show it as a transmission line. And then you have your load. And I'll call this ZL right here. So this characteristic impedance you need to get for the mode. So it would be for the TE10, I think, in that one, right? Now, we might as well do the whole thing. Why don't you just give me a I like to do one of these problems, especially if a lot of people haven't done it, just because I have a feeling you're going to wait until Thursday or something like that, and then the sky's going to fall out. Go ahead.
The waveguide is used to connect an 8.2 gigahertz.
Hold it. 8.2 gigahertz signal. Go ahead.
10 volt source.
Yes, it's 10 volt.
Having a source resistance RS equals 200.
200 ohms. Go ahead.
And then load resistance RL equals 100 ohms.
So it's just RL. RL equals 100. Go ahead.
Waveguide dimensions are 22.86 millimeters.
All right, let me draw. This is the cross section. So here, this dimension is A, and it's 22 on what?
86 millimeters.
And the height?
10.16 millimeters.
Okay.
The length is 0.482 meters. That's airfield.
Oh, good. All right. So think of it as a transmission line problem. The only difference is now we need the characteristic impedance of that guide, and we need beta down the guide. It's no longer just the standard beta omega times square root of mu epsilon of that. You all with me, class? So for this one, first we get the cutoff frequencies, and this is FC, M, and we got to find out what mode we're working in. If we have more than one mode, this problem's kind of a wash. It better be just the 1-ohm mode. All right. So we figure out what these modes are. And that's really equal to, since it's air-filled, it's C over 2. Then you have the square root of M over A squared plus N over B squared. Everybody agree with this? This is just establishing what the cutoff modes are based on the inner dimensions, the cross-sectional dimensions. With me? All right. For this one, a 1-ohm mode is just what? C over 2A, right? And C is 3 times 10 to the 8 meters per second over 2. And A is 22.86 millimeters times 10 to the minus 3. So what's that for the 1-ohm mode? The 2-ohm will be twice whatever it is. Anybody? 6 something? I forgot exactly. 6.56? Is that right? 6.56? Alright, so that would be 6.56 gigahertz, right? Alright, that means the FC 2-ohm mode. Now, I have a comment about this. There's a reason I'm doing it. That's going to be just twice that. It's 2 times FC 1-ohm And so what's twice that? That's what? 13 point, what?
Yeah, 13.12.
13.12 gigahertz. And then the next highest mode, I believe, is going to be FC01. And that's really going to be C over 2B, right? So it's 3 times 10 to the 8th over 2, and B in this one is 10.16 times 10 to the minus 3rd. So what's that? I want to do this to show you something.
14.75.
Now this is the way it is for all these standard waveguides. Like this guy right here, you'll notice the horizontal width is more than twice the height. You all see that right there? What it means is the reason it's done that way, the first and second mode will be the 1.0 and 2.0 modes. Then after that, the 0.1 mode. That's the progression. And what they're going to do with the way they operate this, anything beyond 6.56 gigahertz will pass. Y'all follow me on that? It will pass. But you don't want to get a frequency higher than 13.12, or you'll have 2 modes, 2 different propagation velocities, and you don't know how the power is going to split. Y'all with me on that, class? Now, I showed you this to this is the standard way these things will just develop, the modes. It'll be 1.0, 2.0, and then 0.1, almost always. For this mode right here, the only way propagation occurs is if we're above that frequency. We're at 8.2 gigahertz. It will propagate, and it's only the 1.0 mode. Everybody got me, class? It's pretty straightforward if you think about it. This is a high-pass filter. Now, the next thing we need is the characteristic impedance. That's going to be Z for the, I'll call it TE01 mode. That's going to be the characteristic impedance of the guide. It's air-filled, so it's 120 pi. And it's divided by K. Here, K itself is equal to the square root of 1 minus the cutoff frequency is the 1.0 cutoff frequency, which is 6.56, divided by the frequency of operation, which is 8.2 gigahertz. And you have to square that. So what's K? Just might as well do the whole thing. So this is 120 pi over whatever K is. Anybody do that to me? What is it? 0.6. 0.6. And I don't know exactly what that is, but close to 200 pi. Can you just tell me that? Give me it in the whole. Let me just do the whole thing.
It is 200 pi.
Is it 200 pi? Anybody? Or I mean, just give me the number down here.
Okay.
628. 628 ohms. We'll round it to that. Now, after that, I've got my characteristic impedance. This is the important part right here. Now, I'm going to go ahead and I'm going to get the input impedance right here. So this is my Zn. This is what we're talking about on Friday, I believe, right? So the characteristic impedance right there, let me erase this too. This is just a standard equation you would use for a transmission line, but we're going to change Z0 from that of the characteristic impedance of the transmission line to the waveguide. And we're going to say Zn, and that's right here, at this point. Zn is equal to Z0, and that would be for the TE mode. I'm just going to leave the Z0 there, over Z0 plus J, then ZL, in our case RL, times the tangent. Make sure you put beta Z or something that indicates it's not just the standard beta. That's beta along the guide. Then it's going to be that times the actual length over Z0. So this should be ZL, and this should be Z0. My bad. And this would be Z0 plus J ZL times the tangent here, we've got Z naught. Our ZL is actually 100 ohms, right? Now we've got to get beta Z. How do you get beta Z, anybody? What is it? It's beta unguided, right? Times what? K. Is that? How many remember that? Beta, it's really beta Z, but beta Z is beta unguided times K. What is beta unguided? How can we get it? Remember, it's air. It's really omega times square root of mu epsilon, right? That's the normal way. If it's an air, it's omega over C times K. Isn't it, class? So what is that? Please give that to me. I want to make sure you have all these numbers. You follow me on this? Beta is normally what? Beta unguided is just omega times square root of mu epsilon if it's lossless, right? Square root of mu epsilon is 1 over C. It's air. That's what I'm trying to show you. And K is that K, 0.6. So, anybody? I'm glad you asked this. I want to make sure we go through this one time thoroughly. Yeah. 103? Anybody else? 103? So that's 103, and that's radians per meter, right? You got that as beta Z. Okay. Now, here's where you get your calculators out, and here's the big mistake people make, is in this calculation. Trust me on this one. I guarantee you, I'll give you a quiz this Friday. I think it's going to be Friday. And almost assuredly, about 15–20% of you will have the right stuff over there, and they'll mess up the solution of this equation. You all hear me? So please make sure. If you got your calculators, go ahead and do it. And tell me what you get for Zn. And you can give me simply real and imaginary part or magnitude and phase. Either one. Doesn't matter. But do this calculation. I promise you, you're going to be thanking me. And remember, that tangent is in radians, not degrees. Y'all follow me? Tangent here and here is in radians. So when you take beta times L, speak of that, what is L? 0.482 meters. That will give you a radian value. Y'all hear me? I'm warning you about this because people, they come to me after that quiz or after the test and they say, oh, my calculator messed up. No, you messed up. Your calculator's fine. You don't know how to use it. You got to make sure you know how to use it. Go ahead. Did you have a question?
For Z0,
characteristic impedance, remember that?
Yeah.
All right. It's over here, right? That's ZT is Z0.
Okay.
That's all it is. It's the characteristic impedance of the guy. I'm calling this Z0. The reason I just leave it as Z0 is I don't feel like writing ZTE01. I mean, we know it's in the O1 mode. That's all it is the characteristic impedance, just like a standard transmission line has a characteristic impedance.
Is it O1 or 1L? Yeah, because you wrote
Or 1L. 1L, sorry. 1L, my bad. 1L, sorry. If that was causing you a problem, I apologize. It's just, it's the lowest order mode's characteristic impedance. Remember, that does change with the frequency of operation. That's the difference between a waveguide and characteristic impedance or a standard transmission line. That doesn't matter what frequency you're at. Give it a try.
I got 148 minus J 430.
148 minus J, what was it?
J
430. 430? Ohms? Anybody else?
Something like that.
You got it? You got it? Anybody else? How many? I bet there's at least one person here that didn't get it. Just based on the past experience I've had with this crazy stuff. So please do.
So I guess for transmission lines, all the stuff like Z and all that, those were derived in what they were propagated along. So just your chunks are waveguides.
Yeah, they do. Matter of fact, everything works for waveguides just like transmission lines, all right? With one thing you got to keep in mind though, the guide impedance is a function of frequency. It's not constant. It changes. Every time you change the operational frequency for constant cross-section, that impedance changes. And that's a big deal, as well as beta along the guide changes, because K changes. So it's not just like them, but at a given frequency, you can go through the whole thing, same exact analysis. You can do any kind of matching that way. And we do.
So between like the 1.0 and 2.0 modes, they propagate with the exact same patterns, just like impedances or
Yep.
the next mode.
Actually, impedance goes down. Hey, this is something I want to mention. I didn't say this. If you look at the waveguide impedance, all right, you see how it's just the characteristic impedance of the media, which is, if it's air, it's 120 pi divided by K. But the value of K, I mean, I'll put it down here. K itself is equal to the square root of 1 minus FC over F squared. You'll notice when you're at cutoff, when FC is equal to F, you're operating at cutoff, this is 0. And if you divide anything by 0, it goes to infinity. The impedance of the TE mode as you near cutoff goes to infinity. Now that's why you don't operate just above cutoff, because frankly, you're going to have an enormous impedance to try to feed. And the higher you go, the closer the impedance gets to free space. All right, just remember that. All right, now for TM, it's the exact opposite. For TM mode, it's K times the intrinsic impedance, and for TM mode, as you approach cutoff, it goes to 0. You can't feed a TM mode at cutoff. You can't feed a TE mode at cutoff. You'll get nothing in there because the impedance is not in. All right, you all getting about that? All right, here's the question you asked. So how do I, well, that's ZN. Now the next thing is how do I get this voltage right here, right? V prime. That would be the voltage that will be at the inside of that transmission, or that waveguide. And what I like to do is this. Just draw a simple circuit representing that. And this is the way Dr. Wentworth's book does it too, for the transmission line. Here's my voltage source, right here, and that's 10 volts, right? Then I have a source resistance here of 200 ohms. And now I have my ZN right here. And what I want is this voltage right here. That would be my V prime. Can you tell me what that is? It's what? It's just equal to 10, right? Then it's times Zn. My Zn is 148 minus J 430. Over, then it's going to be 200 plus 148 minus J 430. And you can give that to me in terms of a magnitude and an angle, if you don't mind. It'll make it easier. Y'all follow me what I've done there? Simple voltage division, correct, class? That's it. I want the voltage here. I start with the source voltage. I'm getting calls from all the wrong people. I'm sorry. Do you guys get these things that take a short pole, or your car insurance is run out? And, I mean, how do they know? I didn't tell you guys that. The best one I got is, you want to pay off your student loan. I thought it was canceled. Anybody? Magnitude of phase.
8.2 at an angle of minus 19.9 degrees.
Anybody else? You got that? All right. Once we have that voltage, we're almost done. Now remember, that's the voltage at the input right here. That's equal to it's equal to the forward and reverse traveling waveforms at that point. So then I come down here, and I'll do it right here, now I can say that that V prime right there, which is equal to 8.2 at an angle of minus 19.9 degrees, that's equal to V0 plus, and it's times, now we're evaluating this at Z equals minus L. Because remember, the length of this thing is L, this is Z equals 0. So this point right here is Z is equal to minus L. And normally we would have e to the minus j beta times Z, but because Z is negative, it's e to the plus j beta Z times L, plus the reflection coefficient of the load times e to the minus j beta Z times L. And I didn't get the reflection coefficient of the load, but how do you do that? You take the impedance you're going into, which is Z, I'll put it here, it's going to be ZL minus Z0 over ZL plus Z0. So my Z load was 200, or no, 100. So it's 100 minus the characteristic impedance, which I erased, whatever it is, 628 I think, right? Over 100 plus 628. And you can give me the reflection coefficient. It's strict real and it's negative. Y'all follow me on what I'm doing, class? Remember, that's the characteristic impedance of the waveguide, which is, I think, 628, right? 628 ohms. And anybody?
Negative 0.73.
All right. Now we have this, and now what we have to do is get V0 plus. So if you don't mind, help me out here. V0 plus is equal to, and it's going to be 8.2 at an angle of minus 19.9 degrees. And then I have to divide it by e to the j beta Z times L plus the reflection coefficient times e to the minus j beta Z times L. And that's going to be a magnitude and an angle. If you don't mind giving it to me, I'd appreciate it. So not one you can look at and figure. Pardon? I erased beta Z, I'm sorry. What was beta Z, anybody? 103?
Yeah, 103.
Remember radians, right? Radians per meter, not degrees. Radians per meter. So you got degrees on top.
Oh. That's radians.
Promise you, this problem, I have had nothing but trouble with student calculators in this problem. This type of problem.
Degrees. Gets you every time.
You get it, John? Remember, you're going to be doing this for quiz. It's smart to try to get the bugs out of your calculations now. You can see how this can be irritating. Yeah.
8 volts at an angle of 58 degrees.
8 volts at an angle of 58, did you say?
Yes.
Anybody else? Anyone? You got that? All right, good. Got 2 confirmations. If you didn't get it, don't worry. I'm not saying this is right, but I'm going to say it. If I just ask for answers on this kind of stuff, I get the most incredible spread you can do. And the real thing, too, is round off error can really kill you on this one.
Victor, that one I got.
You got it. You don't have to calculate. Bring it next time, please. He's got 8 volts at 8 at an angle of 58 degrees volts. All right. I'm going to believe that's true. I put the answers down. I didn't put the answers, I don't think, to every single part here, but the final answer I gave you. And so we got that. Now that I have that, where do I do? And let me erase this to give myself a little room. All right, well, now I need the voltage at the load, right? Remember, the general equation for voltage on a waveguide or a transmission line is going to be the form V0 plus, we just calculated that, right? Then it's going to be times e to the minus j beta z times z plus the reflection coefficient times e to the plus j beta z times z. That's what it is. Our load is at z equals 0. The reason we do it is because it makes life easy when I go ahead and analyze what the voltage is at the load. If I take a look at this, z is 0. That means voltage for z equals 0 is the voltage at the load. And that's equal to simply V0 times 1 plus the reflection coefficient at the load. Y'all follow me? All right, now can you do that for me? You've got this value here. So just multiply it by 1 plus the reflection coefficient. Did I erase that too? I guess I did. What is the reflection coefficient?
Negative 0.73.
Okay. So now, what is it? .26 times V naught? Just give me the value. 0.27? And it would be technically at 58 degrees, but we don't care about this angle now. Now we've got the voltage. That voltage is a peak value, right? Now, how do I get the power dissipate? You all agree with that voltage, class? How do I get the power? Remember, this is a peak voltage. That's a pure resistor, right? How do we get power if we got AC peak voltage? Power at the load, well, technically it's 1/2, right? It would be the real part, technically, of V times I conjugate. If you had Dr. Gross, you'd want you to write that. All right? I don't want you to write that. I know power at the load, average power at the load, too, I might add, not peak. Average power at the load is going to be 1/2 magnitude of V at the load, that's the peak value now, divided by R at the load, because it's an AC phenomenon, this is a peak value. So it's 1/2 times 0.27, and it's going to be squared over 100. So what do you get for that? This is the whole problem. We've done it all. What did you get?
We got 2.16 for the voltage.
Sorry, 2.16 here, my bad. Oh,
The angle's right there.
2.16.
Yeah.
2.16.
Yes.
Thank you, 2.16. That means this is 2.16. All right. Y'all follow me? What I'm doing here? Anybody? I got another question for you since we're done this. We're gonna move on. What'd you get? Yeah.
When you talk about average power, are you talking about that average power over a half cycle?
It's independent of any time or cycle. Average power, there's peak power, right? That's the maximum possible value of power, time varying quantity, right? Average power is considered this much. It is, if you took power and you averaged it over a very long length of time, that's what average power is. It's simply the integral of the peak power over one cycle divided by the length of one cycle. It's just the standard average.
23.4 milliwatts.
Anybody confirm that?
Yeah.
Okay, now, hopefully those answers jive with what I put up there on OneNote. But make sure you know how to do this problem in its entirety. Because here's what I can do. I got one more question for you. Think about what I'm asking. All right. What would be the phase velocity in the guide? Phase velocity. Not you guys. How do I get phase velocity? Well, in free space, what is phase velocity? If we have air, it's 1 over the square root of mu epsilon, right? That's c, isn't it? That's phase velocity in free space, correct? For air or a vacuum. When you're in a waveguide, what happens? The phase velocity, this is free space phase velocity. The phase velocity in the waveguide is c because it's air filled divided by k. Isn't it, class? Do you remember me saying that? All right, what is that? Well, 3 times 10 to the 8th over k. K is 0.6 something.
0.6. Exactly. It's 5 times 10 to the 8th.
So it's 5 times 10 to the 8th. Now, phase velocity technically is omega over beta sub z. That's what it is technically. All right? Beta z is along the guide. If you wanted to know what the group velocity was, I actually did this with Zach in my office. Group velocity technically is the derivative with respect to beta z of omega. Really, the way it's given is 1 over, and its derivative beta z with respect to omega. That is the definition of group velocity. You don't have to do that. I'm just going to tell you what the answer is. The group velocity itself is simply free space phase velocity, or c. This would be in the airfield guide times k. Now, group velocity will never exceed the speed of light, or the speed of electromagnetic propagation in the medium, unbounded medium. Never exceed. It's always less than that. So k is 0.6, so that means it's 0.6 times 3 times 10 to the 8th, right? So what is that, 1.8 times 10 to the 8th meters per second? All right. So it's less than the speed of light. But the way you get this, remember this, phase velocity is always the velocity in the unguided media over k, if we're talking about in a waveguide, and a waveguide group velocity is just the velocity of the wave in an unguided media times k. The group velocity, you'll notice, goes to 0 at the cutoff frequency, because k goes to 0. The phase velocity goes to infinity. Just remember those simple facts.
So the velocity, is that the speed of the wave as it goes down the wave?
Yes, that is the speed of electromagnetic energy. That's the key thing. By the way, that's the only thing we really care about. How fast real energy moves. Phase velocity is kind of a fictitious thing, but, well, it's not fictitious, but it really doesn't do us any good. But just realize those two things. You don't need to do this. We did this in my office. That crazy derivative took a little time. But okay. Now, any other questions before I'm going to move on? Next thing I'm going to talk about is slab waveguides. I send you that video. Please watch it. It's a very good video. And I'm going to go through it. There's a couple of different ways that when they talk about a slab waveguide, it's not, I mean, the metal conductor has absolute boundaries where the E field, EZ, or the E field parallel to the actual surface and tangent to the surface is 0. And it makes it easy to solve the del squared equations. Not so with slab waveguides. So these are really dielectric waveguides. They call them slab. Now, fiber optic is a special type of dielectric waveguide, but it's circular. So for a slab waveguide, here's what really goes on. They have material, and they're going to have some epsilon 1. Sometimes they just use N1 for the index of refraction inside this region. This region is usually shown as being 2D thick. That's how thick it is. They normally call this the X direction, and they'll call this the Z direction. And they'll assume that they'll have some epsilon 2 out here, epsilon 2, or really an index of refraction N2 and N2 here. But it is a slab. It's a sandwich, basically. Now, this dielectric, epsilon 1, the core in there, is always larger than epsilon 2. So epsilon 1 will be larger than epsilon 2, or this thing won't work. And here's what really happens. Well, there's two ways to doing this. Before I solve the EMAG equation, to start to at least, they get unwieldy and they're transcendental. They don't have closed form solutions. You have to see where two different trajectories overlap to get the answer to these things. But here's what's really happening. First, we're assuming if that's Z and that's X, Y is out of the board. They don't care about how big Y is. They're assuming that this thing's a sandwich and Y is very, very wide compared to the height D. Y'all follow me? And they assume that the solutions have no Y variation, and that's a very fair assumption. Right? But what happens is the wave ricochets all the way down here, just like it does in an actual perfect electric conductor guide, just like it does in the ones I've been showing you. Okay. By the way, where are those the wave guides? Oh, I want to make sure I don't forget them. No more. Everybody get a look at these things? You guys? Okay. Now, what do you think limits this angle right here, where this is, call it theta in here? Just give me an idea. Remember we talked about the critical angle? Right? It's the angle for which, if it gets any larger, the entire wave is reflected. Do y'all follow me? So here's the whole deal with these things. They're going to feed optical light, I call it light, but really you can have electromagnetic energy that's not truly optical, much lower frequency, at an angle into this guy so that this angle will be at the critical angle or greater. So it'll bounce like this. Do y'all follow me on this, class? Now, if they fed it straight up and down, it won't work. It'll penetrate, there'll be no reflection. But what they do is feed it at an angle that's the critical angle or less. Now, there are two possible modes. There's both a TE mode, that's with the electric field out of the board, bouncing this way, or the TM mode, where the magnetic field's out. Do y'all follow me? The critical angle is the same for both, so you don't have to worry about that. The reflection coefficients are different in general for TE versus TM, but you don't need to even worry about them yet. Now that's the essence of what happens when they talk about what's called a bounce diagram analysis. I want to just tell you where this is in Dr. Whitman's book. And I have my own take on why some of this is very unsatisfying, but in terms of the analysis, but it's true. This is on page 398. And what he does is he shows the standard bounce diagram, and they're going to figure out what these angles are so that they get complete constructive interference with this waveform. In other words, it's going to hit here. By the time it bounces there, if you drew a parallel line there, the phase on this one would be constructively added to that, where they'd be out of phase by exactly 2 pi radians. Now they have to take into account the actual effects of the reflection coefficient. I'm going through this hand waving thing just because before I get into the deep math, you have to have an appreciation of what's really going on. And here's the deal too with this stuff. Anytime you have materials of different electrical permittivity that are placed in really on top of one another, you get something, an interface that will cause electromagnetic energy to fly along it. And in this case, it's just going to bounce in and out here. It just happens. Now, something that now we have talked about before we get into the solution to all the equations is what actually happens in this material. These are dielectrics. And you could think of the inner material of like glass, and maybe the outer material just air. That'll work. You'll get something bouncing like that. It's a slab waveguide. But here's the difference. When you have these two materials like that, if you were to plot the magnitude of the electric field, say this is going to be X direction, and this is going to be, say, Z direction, right down the center. And this is going to have a width of 2d here. And again, this has some epsilon 1 in this center, and epsilon 2, epsilon 2. Now, if you looked at the magnitude, let's talk about propagation here. For this one, let's say we have a TE mode. TE would be E field out of the board in the y direction. So if we take a look at a TE mode and we have plotted just the magnitude of EY versus the height, now if it was a perfect electric conductor, it'd have to go to 0 there then. Y'all follow me? The slab's got that much thickness, so this is the slab itself in there. It would have to go to 0 if that was a perfect electric conductor, because EY, right, EY would be tangent to that. Y'all follow me? Not so in a slab waveguide. What you get is this. This would be for an even mode. You'll get a magnitude that'll do that. It will not be 0 right here. And what happens is this. That's the magnitude of EY. Now I can show you the solution to this in a second. But what happens is that the electric field will bounce back and forth all the way there, but will also create what's called an evanescent mode there and there that will exponentially decay. But all that energy in this field will collapse back as this thing cycles in time. Think of a capacitor for a second. You know, when you have a capacitor, you have electromagnetic energy in the field. Then it collapses in the field, collapses. Do y'all follow me? As you go through a charging cycle. Nothing is dissipated. It exists, then it goes back in. That's a type of evanescent field. Out here, the field created will collapse back in when it goes to 0, and it will not propagate this thing. Right? That's the thing you have to appreciate about this. The wave will propagate this way, but the field values don't go to 0 right there. So now the solution to this gets a little hairy. That's the reason I gave you that video. That'll help, but I'm trying to set you up for it. So what they normally do is this. When they're solving these things, they always start with Maxwell's equations. I'm not going to start at that point. But they're going to come down to, they're going to get a second derivative of the E field plus beta squared E equals 0. This would be, this actually would be for the TM mode, TM modes, right? They're going to do this. Then they'll come down here and they'll start solving this as second derivative of E, I'll call it EY with respect to x squared plus second derivative of EY with respect to z squared plus beta squared EY equals 0. Just bear with me on this one. I'm not going to go through the whole separation of variables things because right now it wouldn't help you to understand this. This would be the standard constant, beta x squared minus beta x squared. This is the standard constant, beta y squared with a minus sign. We don't have, I'm sorry, this would be beta z squared, my bad. Beta z squared, beta x squared. We don't have a beta y there because y is infinite. You can assume it's infinite, it has no variation. Now come down to here, and then, remember at that point we did separation of variables. Y'all remember this? And then we found out the solutions could either be sines or cosines or exponentials. Y'all remember that? Same deal goes here, but now something odd happens. There are two types of modes for the for TM propagation. You can have modes where they'll be even. In other words, if we plot the magnitude of the E field here versus the height, an even mode would look like this, where it would be basically the same above as below this. An odd mode would look like this. It would come up, and then it would go to a 0 and come this way. That's it. That would be an odd mode. Do y'all follow me on this class? There's even and odd modes that are allowable. Even or cosines, odd would be sines in the inner region. So what they do is they'll say that EY in general is going to be some constant, and I think they call it like normally A times cosine of beta x times x plus, and then I'll call it C times sine of beta x times x. These two things are going to be multiplied by a propagation term, e to the minus j beta z times z. And this would be for x, magnitude of x less than b. So it's in this region. Now don't worry, you're wondering about some of this stuff. This will come together. So it's inside this region. Y'all follow me on that? Now, outside of that region, EY will be equal to some, and you can call it d times e to the minus alpha x. And this would be for x, magnitude of x greater than b. And EY here would be equal to, really it's going to have the same exact form. It will be b, and it will be e to the alpha x. And that would be for magnitude of x, or really for x, sorry, not magnitude. This would be for x less than b. This is above, this is below. And it would have the same e to the minus j beta z times z. Just give me 1 second, I'm almost done. All right, try to appreciate one thing. And this is the key thing. This is for the mode with TM, talking about the E field itself being perpendicular to the plane propagation. But just hear me on this one. When you take a look at this, what you have to do is match the boundaries of this equation to this equation at x equals d. Y'all follow me on this? Just try to understand. That will become d, that's d, and that's d. The e to the minus j beta z times z cancels. Forget it. You have to do the same down here. Now that's just for the E field. When you watch the video, make sense of this. It'll help you a lot. Then you have to take the curl of that to find the H field. Curl of E is minus j omega mu times H. Then you have to have the tangent H field to me. Y'all follow me, class? Then after that, you have to divide the E field by the H field. And you get what are called transcendental equations, the solutions of which you find by graphing one equation and then graph the other. And where they overlap, that's the solution. Y'all follow me? Now it's complicated. I'm going to make it a lot easier next time we meet. I'm going to go ahead and just show you the important thing to get out of this whole thing. But please watch that video from me. If you watch that video, I'll do you right. But if you don't, God help you.